Hello everyone. So if you're watching this video, you are either most likely taking organic chemistry with me as your professor, or maybe you just are reviewing organic chemistry. You took it a while ago, or you just stumbled upon this video. But either way, what I am presenting and teaching is using this organic chemistry textbook available through OpenStax, which is an open educational resource textbook, which all that means to you is that it's free, it's available online. You can print it if you want, but it's online and it's never going to be behind a paywall or anything like that. So in this first chapter, we are starting by reviewing structure and bonding. Now I say reviewing because you learned a lot of this. However, I understand that it's not easy to remember a lot of this, especially if you took Chem 1 and 2 maybe several semesters ago or several years ago. And sometimes it's just you learn so much in college that kind of you learn things in one semester and then the next semester they get pushed out because you're just learning so much. So I understand that, and I'm keeping that in mind when I'm teaching things that you may have already learned. I'm just gonna keep it like one level. We're all starting from the ground up. If you find that it's kind of boring, it's repetitive, skip through whatever you feel like you already know. And if you don't feel like you're too confident about any material, then stick through the videos. I will walk you through it. So I have a meme here already on slide 1. So organic chemistry, you'll be drawing a lot of hexagons, especially if you also take organic 2, very heavy in that class. And by the end of it, you'll probably feel like this meme is showing, like Tom Hanks in this movie, which I'm actually blanking on the name right now. But he's tired. He's been on an island for a while. He's been surviving, but he's clearly been through it. You might feel like that, but when you look back, it'll be worth it. So why are we studying organic chemistry to begin with? Obviously, this is probably in your degree plan, or most likely, this is a prerequisite for some sort of application you're going to complete. Medical school, pharmacy school, PA school, vet school. There's a lot of different professional schools, or graduate school, or if you're completing a chemistry bachelor's degree down the line, like if you're completing your associates and then your bachelor's in specifically in chemistry, you would need organic chemistry. So there's a variety of reasons, right? I listed many. However, as a learner, why do we study organic chemistry? As a scientist, why do we study organic chemistry? And as a scientist, we know that biology is the study of life. And when you look into the chemistry of biology, we see that every living organism is made of organic chemicals. So the proteins in your hair, the keratin, your skin, all your muscles, they are made of protein, which is an organic compound, right? DNA that controls your genetic heritage, that is a very long, complicated molecule, basically, that is made up of, it's an organic compound. Foods that nourish you, all organic compounds. Medicines that heal you are organic compounds that were once studied for a really long time to end up being a medicine that's approved and safe for you to consume. These are all organic chemicals, right? So they are everywhere, involving us and feeding us and healing us, right? Most importantly, feeding. That's why I have some tacos here, but keep this in mind that they're all around you. So some examples of some organic chemicals that we use in the real world that you've probably heard of. So OxyContin, unfortunately, it probably has a negative connotation in terms of you hearing about it. There's some shows on Netflix about it. I think the one I watched was Painkiller. That one was super interesting. Definitely recommend. Also, The Pharmacist. That one was a documentary, and it's about OxyContin. So there is an opioid crisis occurring here in the US, unfortunately, and it's mostly surrounding OxyContin. More recently, I think fentanyl. But OxyContin is a pain medicine. This is the structure of it. It's kind of a complicated structure, but it's made up of mostly carbon atoms and hydrogen, oxygen, and some nitrogen. And this is what we consider organic compounds. We also have cholesterol. So cholesterol is something you hear of that's in your body and that you eat. There are good cholesterols, there are bad cholesterols, depending on the structure. That's how they act in our body. But the general idea, this is the structure, and you can see here it has a lot of carbon, hydrogen, oxygens. And then we have penicillin, and penicillin is a common antibiotic, and it's, I think, one of the first antibiotics that was like mass produced, and it has a lot of carbon in it, also sulfur. You'll learn more about which atoms are common in addition to carbon in organic compounds. And while these may look really crazy and unintelligible, by the end of the semester you will be able to make sense of them, and they'll be not necessarily no big deal, but you will understand what everything means. So you might have heard me mention organic chemicals have certain elements in them, right? I said carbon and oxygen and those other atoms in the examples I just showed on the previous slide. But what does organic mean? I once had a coworker in college ask me what I was studying, and I said organic chemistry, and they made a joke about like organic vegetables, and that did not compute in my brain. So it was very much, this is how I felt, like this mocking SpongeBob, because I wanted to tell them, no, this doesn't reference organic, like organic produce and conventional produce. What we mean by organic is, it's a historical term that comes from the mid 1700s when it was used to describe the chemistry surrounding living organisms. Kind of like what I discussed earlier, organic chemistry has to do with compounds that are typically found surrounding biology. So to scientists at this time, organic substances isolated from plants and animals seem different from those that were inorganic, which are minerals, salts, any type of rock. Those are all inorganic substances. So what does organic mean then? By the mid 1800s, we found that there was not a clear fundamental chemical difference between organic and inorganic compounds. They were following the same chemical physical rules, right? It's all chemistry. However, it's just a label. This is organic, this is not, right? The only distinguishing characteristic of organic compounds is that they all contain the element carbon. So the element carbon is here in the periodic table. It's towards the right hand side in the second period. And you'll see why carbon specifically is so special in future videos, I believe. Yes, in a future video. But what causes this unique, special characteristics to carbon is that it can share 4 valence electrons and it can form 4 strong bonds because of this. And because of this, or ability to form bonds in 4 different ways, you can form chains, you can form rings. There is an immense diversity of compounds, organic compounds, because of this. So here in this periodic table, what this is showing you is the carbon, obviously, and the typical elements found in organic compounds. Usually you will not see any of these metals on the left hand side of the periodic table. Very, very rare. What you will see very often is hydrogen, nitrogen, oxygen, fluorine, and these other phosphorus, sulfur, chlorine, bromine, iodine. And these are the colors that are typically used in textbooks, in chemistry learning resources. These are the colors used to represent these atoms. So again, we are reviewing some atomic structure. What you learned in Chem 1 was that there's a nucleus and then there is an electron cloud, basically. And the nucleus contains the majority of the atom's mass. It contains the protons and the neutrons. This is what makes up an atom's mass. The electrons, on the other hand, the weight of them is negligible. They are very, 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 very tiny. And they occupy this huge space in comparison. The scale of this is like if the nucleus was a blueberry in the middle of a baseball field. And everything else is, the entire baseball field around it is where the electrons are. They can be. Electrons, again, they occupy most of the volume. So again, think of the baseball field. They're all over. They can be anywhere inside that baseball field, or stadium, but they're very small. The diameter, very tiny. It's in the -10th power of meters, which is very, very small. And as you increase or get closer to the nucleus, the electron density increases. And it's 40 times greater being closer to the nucleus than outside over here in the rest of the atom. So I have a simulation to show you. It is linked within your PowerPoint slides. And you just click here and you will see this screen. Specifically, you're going to choose build an atom and you're going to choose the atom selection. So here I have the simulation open, and like I said, I'm going to click atom. Now, what you see here is the ability to build an atom, like the title of it states. You have protons, you have neutrons, electrons. You have here a periodic table. It's going to show you what element you're building or going to build. You can expand these 2 sections to show you the charge and the mass number. You can also click between orbits and cloud. You can play around with it and find, maybe it has some features I won't exactly mention, but what I want to show you is where the protons, where the neutrons, where the electrons go, and how that makes an element, to remind you what you learned in Chem 1. So when you get a proton and you kind of throw it at the atom, you'll see that it automatically goes to the nucleus, right? That's where it belongs. and it'll start telling you the name of the element and whether it's an ion. Here, this is an ion because we only have protons. We don't have any electrons to neutralize the charge. Now that I have 2 electrons, this neutralizes the atom, and it's a neutral atom. You see, I have 2 protons, 2 electrons. If I add neutrons, what I'm basically doing is creating different isotopes of this. If I add more protons, I am looking at a different element. You see how the name is changing? Now, I finally got to carbon. It has 6 protons, and right now it's an ion because I don't have enough electrons. And you'll see that it's not wanting to add. Oh, there it goes. It added the full 6 electrons to completely neutralize the atom. However, it usually has 6 neutrons as well, and this is what the mass number is. The net charge 0. This is a neutral, stable carbon atom. Again, there are isotopes that exist where that is where you have more neutrons or less, and when it has more or less electrons, it turns into an ion. When it has more or less protons, it's a completely different element. So this is just a short, quick review visually of how the structure of atoms are and how it works.